we've been now talking about the idea of the electric force, and that there are these two properties that are affected. Whether something has a positive charge, something has a negative charge, they'll be affected by this electric force. But today in class we actually talked about how to quantify that electric force. And in 1785 you had Charles Coulomb, who actually was trying to figure out what this interaction was between these two charges. And what actually ended up being discovered was that, a few things, the force is always directed along a line between the two particles, if you are assuming particles, okay? Point charges, if you will, charges that would be able to be modeled just a point in space, like a particle, for example, an electron or a proton. And if you have two of these particles, say one with charge Q, and the other one also with charge Q, okay, positive charge Q, he noted that if you have them of the same sign, that they will then repel each other. If they have opposite sign, they will attract each other. And of course that force will be directed along the line between those two things. He also noted that if you increase the value of one of these charges, the force itself will increase in the same way. You'll have greater attraction or have greater repulsion. And then if you change the distance by which they're separated, which the separation distance we would call r, then as you move the charges away from each other, the force drops. And it drops as a square of the distance. Or, if you put them closer together, it gets stronger, and it gets stronger by the square of the distance. So it goes 1 over the square of the distance in that way. It's an inverse square law. So putting all this together, what he realized was that the force you get due to this idea of electric stuff, the charges of these particles, is equal to, let's call this one Q1 and that one Q2. The magnitude of this force is equal to the multiplication of both the two charges, Q1 and Q2, their magnitudes, divided by the distance between them squared. That's not the full story, though, because he realized that you wouldn't just get this simple relationship. There was a multiplicative factor that was involved, too. That multiplicative factor is a K sub E in order to fit in with the idea of electric forces. And that K is 8.99 times 10 to the minus 9th Newton meter squared per Coulomb squared. And you can prove to yourself that the units you get out of this would be units of newtons, which you would want if we're talking about a force. The question is, you might be thinking, well, what's the direction of the force? This is the magnitude, what's the direction? The direction depends on what is actually happening with the two charges. So if you're talking about the force of charge 1 being exerted on charge 2 here, that would feel a force to the right. If you're talking about the force that Q1 feels here because of Q2, well, that will be directed towards the left. And so you have to be able to know what's going on with these two, with the charges, to know what sign to put in front here for the vector nature of this. Because yes, force is a vector. And so you have to worry about the different components if you were trying to combine different things. And one good thing about the electric force, as was realized, is that you can use the superposition principle, that you can add up the contributions from every single individual charge you might have in a configuration, and take those components, add them together, and you get the overall force. You don't have to set up your configuration, make some complicated mathematical statement that includes all of the charges together and add them all up. You can take each one individually and add them up separately. Okay. So, what does this mean? It means that if we have, for example, a situation where we have charges arranged in a certain way, and we talked about this in class, that say you have a charge here, you have a charge here, and you have a charge here, we can look at the charge of each one. We look at the force exerted by each one on each of the other ones, and we can make a statement about the electric force that they would actually feel. So, let's just say that this one is going to be, I think this is close to the example we did in class, that this one's going to be minus 2, 0.00 times 10 to the minus 9th coulombs. This one is going to be plus 5.00 times 10 to the minus 9th coulombs. And this one we'll say is plus 1 times 10 to the minus 9th coulombs for the charges. Okay. And let's think about what's going to happen here with regard to the forces. Okay, we won't do any of the math to break it down, but we'll think about what's happening with this. So let's think about specifically the forces that are going to be acting on this particle right here. For the moment, we're imagining that these particles aren't going to move, that we've glued them down here somehow, okay? But they're going to stay here, doing electrostatic stuff. But we want to investigate the force that it would feel from being in this configuration. Okay? So looking at this situation right here, this one is negative and this one is positive, and so we know the direction of the force. The direction that this particle would feel pulled, or pushed in this case, it actually is being pulled, would be towards this negatively charged particle, because this is positive and negative, and they're going to attract. Now the opposite situation would happen here, from this particle to this particle, because this is a positive charge, that's also a positive charge. And so that vector is going to be directed this way. And so we see this, we realize this, we're going to have to add these two vectors with their components in order to figure out where exactly the particle would feel that force affecting it. Okay? And so you could figure out the math, basically, to try to figure out what the overall setup is here. Let's say that this is going to be, well, we'll do the same sort of idea we had before. Now, this is going to be 3 meters, this is going to be 4 meters, which means that this one is going to be 5 meters for a nice 3, 4, 5 right triangle. That means that this angle here is 37 degrees. It also means that this angle here is 37 degrees. Okay? So, we have F, this is going to be 1, this is going to be 3, this is going to be 2. We want to look at the force that 3 feels because of 1, or the force exerted on 3 by 1. So that would be F1, 3. And then the force that we have exerted on 3 by 2 would be F2, 3. Okay? And of course we want the resultant force, which would be the addition of those two together with regard to their components, so we can figure out what the actual result would be here for this. Okay? So, what would you do? You would realize that we have KQQ over R squared for this case, where we have the Q is here. We take the magnitude as minus 2 times 10 to the minus 9th coulombs. The magnitude of 1 times 10 to the minus 9th coulombs here. We have to divide that by the distance squared, which is 4. Right? And we have to multiply by that K, the 8.99 times 10 to the minus 9th Newton meter squared per Coulomb squared. And that would give us the force, the overall force, that this one feels from the charge here from 1. Okay? Now we can look at this and we can note that the force is only going to be felt in the x direction. And specifically, it's going to be negative. So we're going to have negative F13 in the x direction. Okay? Just put that right there. Okay, because it's only directed in the x. Now for F23, we're going to have a component both in the x and in the y. They're both going to be positive, as we can see from the sign. And so you can figure out the force from particle 2 acting on particle 3 by using KQQ over R squared, where R is 5. And then that gives you this vector right there. But now you have to figure out what component it has along the x and what component it has along the y. So you would have F23x would be equal to F23 cosine of 37 degrees. And you'd have F23y is equal to F23 times the sine of 37 degrees. And then you would add the x and y's from here and the x and y's from here to get your overall F using our vector analysis like we've done last semester, and then be able to figure out, using the Pythagorean theorem, what the overall force is, and then figure out the resultant angle from the x-axis that this force would be felt at. So I'll let you check that out on your own with the numbers to see where exactly that would be, giving you a good test with these numbers to try to figure out what's going on here. This is similar to what we did in class, but I believe the number is slightly different for the charge, so it'll be a slightly different answer. But the basic idea still holds the same, that you have to look at the forces acting on the particle in question and add them up with their vector components, being careful with the signs, which you figure out based on if it's positive and negative, or if it's positive and positive, or if it's negative and negative, and knowing where the arrows are pointing so that you can figure out what sign to put on your force. Okay? And in the next bit of what we're going to do, we're going to talk about writing this instead of as a force, as a field. We'll get into more details of that in the next one.